So we're going to be talking about systems of equations, or I might say matrices, and dealing with that. So that's our goal for today. Before we get to that, there's of course our thought for the day, and comes from Grand Admiral Thrawn, who is a character from the Star Wars universe. Hashtag Empire did nothing wrong, people might say. But what did he say? Do you know the difference between an error and a mistake? Anyone can make an error, but that error doesn't become a mistake until you refuse to correct it. I see this a lot with students. Lots of people make errors, including your instructor. I know I've made many errors. The question is, what do you do with it? What do you do with that error? Do you let it beat you down and say, okay, I'm just never going to be good at this thing and give up? Or you say, this is a chance for me to learn, to correct my mistake, and to get better. And that's pretty much the difference between people who are going to fail and people who are going to succeed. You can correct your errors. You don't have to make them into mistakes. You don't have to let them bring you down. So don't get frustrated by making errors. Learn from them. All right, now, what is our goal for today? 2 equations and 2 unknowns. So we're starting out very simply. Now you might say, couldn't we start even simpler? 1 equation, 1 unknown? Well, we kind of already have done that. So 2 equations, 2 unknowns. And what does that mean? Well, we have 2 equations here. Ax plus by equals h and cx plus dy equals k. And I've marked the x and y here in a slightly different color just to emphasize these are our unknowns. These are variables. So the other things, the other letters of the alphabet, the a, b, c, d, h, k, those are things we do know. Now, what's the goal? We want to solve. And we want to find the x and y where both of these equations simultaneously are true. And we'll talk about a few methods to solve. We'll talk about graphing, substituting, and eliminating. And in practicality, graphing, beautiful idea, not very useful. Substitution and elimination, those will tend to be our go-to methods. They're very reliable, and we're going to get more and more sophisticated as we go. But at the end of the day, that's really our basic ideas. It's just, what do we want to do? And it says, look, instead of 2 equations, 2 unknowns, reduce to a simpler problem of 1 equation, 1 unknown. And that theme is going to keep going for the next couple lectures. It just says, hey, if I have a big problem, can I turn it into a smaller problem? And then can I turn that smaller problem into an even smaller problem till I get to the point where it's like, there's no problem at all. And if you can, then you win. So, something to look forward to. All right, well, so again, where are we at? We're going to have our 2 equations, 2 unknowns. We're going to emphasize we're doing what are called linear equations. So these look like lines. So this is the generic part, but we can do a specific example. We'll see this several times. X plus 3y equals 11 and 2x plus y equals 7. And again, we're looking for solutions. Where are both these equations true? So we say, well, what are these? If I think about what does x plus 3y equal 11 look like, that's the standard form of a line. And so we can graph it. So x plus 3y equals 11, probably the easiest way to graph is think about where are the intercepts. So if I want to know where it hits the x-axis, you set y equals 0, hits here at x equals 11. If I want to know where it hits the y-axis, I set x equals 0, and it hits at 11/3. And once I know 2 points, I can draw a straight line. And similar here, I can see it hits the y-axis at 7, and it hits the x-axis at 7/2, or 3.5. So we have our lines, they intersect. This intersection is the solution. Now, I've written down where the intersection point is. I didn't have a grid, and this is one of the inherent weaknesses of graphing. You have to be really precise with your picture. Your picture has to be spot on. And oftentimes, very simple looking equations can give you not so pleasant points as solutions. All right, now why is the intersection the solution? It should be noted, any point on this line, this purplish line, is a solution to the first equation, x plus 3y equals 11. Any point on this red line is a solution to 2x plus y equals 7. To say I want a solution to the full set of equations, to both equations simultaneously, because I'm looking for something where both are true at the same time. That's why we're looking for the intersection. All right. Any questions? All right. Well, as I've already said, in practice, solving by graphing is hard, but it's still good for intuition. So we can talk about, what can we say about solutions? So there's a couple of things that can happen. If our lines have, I'll say, distinct slopes, and what do we get? Well, we're going to form a crossing set of lines. They have to intersect. If you're in the plane, if you have two lines, you either have the slopes are the same or the slopes are distinct. If they're distinct, they must intersect. And they must intersect in one place. So you get one solution. And this is called consistent and independent. Now, the word consistent here just says there's a solution. The word independent says there's not a redundancy. So there's a solution, there's no redundancy. We'll talk about redundancy in a second. Well, what happens if the slopes aren't the same? A couple of things can happen. If you have parallel lines, same slope, but they're distinct lines, so maybe they have different y-intercepts, for example. What's going on? Well, these lines will just run on a pair of tracks forever. There's no intersection. Which means in terms of the solutions, there's no solution. So it's possible to come up with a system of equations where no solution is possible. And we call this an inconsistent system. It's just there's no solution, right? Consistent means there's a solution, so inconsistent means not a solution. Now, there is another possibility. They could be parallel because they're actually the exact same line. So they're on top of each other. And now you're like, well, what happens? Well, what happens is that now every point is a solution on the line. So you get infinitely many solutions. So we still have this notion of consistent. Yes, there's a solution, but now there's a problem of redundancy. And that's where this word dependent is coming into play, in that, hey, you really didn't have two equations with two unknowns. You really just had one equation with two unknowns. So there was a dependent relationship between the equations. We don't want redundancies. The ideal situation is one solution, and that's what we'll encounter most of the time. Well, we want to solve. And so our goal is let's figure out a way to solve this, and we're going to solve these algebraically. And we're going to talk about two methods. So, method one, substitution. Well, what's going on? there's an underlying strategy that's always going to be in play. Reduce to a simpler problem. Somehow get from 2 equations to 2 unknowns to 1 equation, 1 unknown. So the idea of substitution says I can use one equation to plug into my other equation to get rid of one of my variables. So the first step is you solve for the variable in one of the equations in terms of the other. So maybe I say, oh, I can put x equals something, y equals something. And now I say I take that information, I plug it into the other equation. With that, I can solve. So what's going to happen is I'm going to have a simpler equation. I can solve that, and then I can use that information to recover what the other part of my solution should be. And then something happens, and then we get profit. Now I will say, among all the steps here, step 4 is the hardest one. It's still the one that I'm working on. But usually we're pretty happy if you get to step 3. Any questions on the ideas before we go to some examples? All right. Well, solve by substitution. So let's start with this one. We have x plus 3y equals 11, and 2x plus y equals 7. Now you get some freedom here. When we're talking about solving by substitution, it says I get to pick one of the 2 equations, I get to pick one of the 2 variables, and then I have to solve for that variable in that equation. Now generally when you're doing that, you say, well, let me look for like a pretty nice coefficient, something really easy for me to work with. So which equation do you want to use? Which variable do you want to solve for? There's not a wrong answer. There are easier answers, but there's not a wrong answer. Let's say we had the first equation. Would you rather want to solve for x, or would you rather want to solve for y? Or does it matter? From a mathematical perspective, it doesn't matter. From a I'm nervous about fractions perspective, I would say solve for x. Because if I had to solve for y, what would happen? So there's 2 things I can do. If I solve for x, that becomes x is 11 minus 3y. So that's what I mean by solve for x. Get x by itself. If I were to solve for y, well, first thing I would do is I say 3y equals 11 minus x. Then I would say I want to get y by itself. And I'd say y is 11 thirds minus 1/3 x. Now between x equals 11 minus 3y and y equals 11 thirds minus 1/3 x, which feels the one that's easier to work with? Personally, x equals 11 minus 3y. No fractions. Sometimes you just have to bite the bullet, but if you can, go with something that either minimizes fractions or has no fractions at all. So here's the idea. We've used the first equation to solve for one of the variables. We're going to take this information now, and we're going to plug it in to the second equation. That's the substitution. We're substituting that information into the second equation. So this becomes 2 times 11 minus 3y plus y equals 7. And remember, this 11 minus 3y is your x. Well, now we have one equation, but only one unknown. There's no longer x's and y's, only the y's. So we can distribute. We'll get 22 minus 6y, still add the y, equals 7. And now we just work on our solving, right? We group things together, move things around. So for instance, the minus 6y plus y gives us minus 5y. So 22 minus 5y equals 7. We can bring the 7 across. We can bring the 5y across. So we get 5y equals 22 subtract 7 is 15, or y equals 3. Now, is this our answer, and why not? What are we missing? We're missing x. So when we talk about the solution, we need to know both x and y. Right now, all we have is y. We do also have a suspiciously big gap, so that's okay. We'll have enough space to finish the problem. So what do we do with this information? Well, we know y. We come back to our substitution rule, because we know what x is in terms of y. So we say, then x is going to be 11 minus 3 times 3, which is 11 minus 9, which is 2. So notice we can use the substitution rule to now figure out the part that we don't know yet. We don't have to restart the problem from scratch and say, oh, now we've got to do another substitution. It's all there for us. So we get our solution. X equals 2, y equals 3. Any questions on the process? Again, we could have gone with this substitution. We would have gotten the same answer. We could have solved for x or for y in the second equation and put it into the first. We would have gotten the same answer. So there's different ways to approach it. So you don't have to necessarily say, which way is going to give me the right answer, because almost anything will give you the right answer. But you should stop and think for a second, which way am I most comfortable in proceeding with this problem? And that's a way to move forward. All right, well, there's a second problem here, solved by substitution. 3x plus 4y equals 7, and 2x minus 3y equals 16. Do we have an answer yet? Someone willing to say, I think I know the answer to this one. Oh, okay, I see a hand. All right. X equals 5. And you said what? Okay, so we have a possible answer. Now, can we move from saying, well, this is a possible answer, to saying like, yep, this is the answer, without doing all the work? If we have a proposed answer, how can we know it's correct without actually deriving it? How do we check if an answer is correct? Well, we have the two equations. Let's plug it in. If x equals 5, we get 3 times 5 is 15. 4 times negative 2 is negative 8. 15 subtract 8 is 7. That's a good sign. 2 times 5 is 10. Negative 3 times negative 2 is 6. And 10 plus 6 is 16. Okay, good. Woohoo! Yes! All right, so that is the correct answer. All right, so let's run through it really quickly. What do you want to solve for? You have the first or second equation and x or y. Second equation for x. Again, there's not necessarily a wrong answer. Now, one of the things that we can do is, if we do encounter fractions, we have ways to get around that pretty quickly. So in this case, got the x by itself by moving the y across, divide by 2. So that means everything gets divided by 2. X equals 8 plus 3 halves y. Now, that information is going to be fed into the first equation. So we're taking this piece here, and we're putting it upstairs. So we're going to get 3 times 8 plus 3 halves y plus 4y equals 7. Distribute through, you get 24, 3 times 8, plus 9 halves y, plus 4y equals 7. So you have one of two options here. You either keep going or like, I don't like fractions. Now, I don't know how you feel about fractions, but I have been burned before by fractions. If you don't like fractions, and you notice that we do have a fraction here, what can you do? You can get rid of your fractions. How do you do it? Well, multiply everything by something big enough to get rid of the fraction. What's something big enough to get rid of this fraction of 2? It's between 1 and 3 if that narrows it down. It's 2! Yes! So if you want, you can multiply everything by 2. So this becomes 28 plus 9y plus 8y equals 14. Now there's no fractions. 9y plus 8y becomes 17y. Now 14 subtract 40, okay, take that across. That's why they invented calculators. 14 subtract 48 is negative 34. So then y is negative 34 divided by 17, which becomes negative 2. Once you have y, put it back into your substitution. Excuse me. And we end up saying, aha, that tells us about x. So x is 8 plus 3 halves times negative 2. And that's the same as 8 minus 3, which is 5. So there we get the x equals 5. All right. Now this is just one way to do it. We're going to talk about a second method. So you're going to have another chance at this problem. Don't worry. And the good news is the next time you do this problem, you already know the answer. So it's going to make it even easier, right? It's nice when you know the answer ahead of time. Things go faster. So, before we get into the second method, the paper is fighting me here. There's an important idea, and this is actually going to be an idea that we're going to lean into in the next few lectures. Which is to say, if we don't like the system of equations we have, we can modify them into a nicer system of equations in such a way that they're equivalent. Now, when we say we have an equivalent system of equations, what we mean, what we mean is that any solution to the first system of equations is a solution to the second and vice versa. So they're equivalent in terms of they have the same set of solutions. So what are some things that we can do? Well, suppose I have two equations. I can just swap the order I write the equations down. And if I do that, it's pretty convincing to say, oh yeah, if I can solve the first system of equations, I can solve this system of equations as well. Because they're the same equations, they're just written in a different order. All right, that seems pretty harmless. A second thing we can do is we can pick one of our equations and say, let's multiply it. Multiply it by a non-zero number. Okay? So here, I took the equations x plus 3y equals 11, 2x plus y equals 7, and I multiplied the first equation by negative 2. Now, what's true? If I have a solution to the first set of equations, I have a solution to the second set, and vice versa. I can go back and forth between. Okay. Now, that one again, pretty harmless. If I multiply both sides by a non-zero, I can essentially undo it. The third one is the big ooh. And this is where the power is going to come from. It says, I could add a multiple of one equation to another. So when you hear that, it's like, wait, what? So let's be a little bit specific. Again, we start with our basic equation. We're going to leave the first equation as is, but for the second equation, I have the 2x plus y equals 7. That's still there. But what I'm going to do is I'm going to add a multiple of 5 to the first equation. So I'm going to add 5 times the left-hand side to the left-hand side, and 5 times the right-hand side to the right-hand side. So that's what I mean by add a multiple of one equation to the other. And then if you expand it, lo and behold, you get 7x plus 16y equals 62. And so the moral here is if I have a solution to x plus 3y equals 11, 2x plus y equals 7, that must also be a solution to x plus 3y equals 11 and 7x plus 16y equals 62. Now you look at that and say, Steve, you have chosen poorly because you haven't followed the mantra, make things simpler. That's true. But I have shown it's possible to do these things. Now, why does it work? Why are these still equivalent? Well, suppose I have a solution to this set of equations. If x plus 3y is equal to 11, what happens to the 5 times x plus 3y and the 5 times 11? They're equal, right? Because that's what the part above here says. Which means that that part goes away and you get down to 2x plus y equals 7. So it reduces down to what you did before. But, again, the key is we must choose. But choose wisely. For as a good choice will make the problem simpler, the wrong choice will make it more complicated. So now we're ready for our second method. Elimination. So the goal is still the same. We want to knock out a variable. But now instead of substituting, we're going to do it in a slightly different method. So here's the idea. We're going to pick one of the variables to knock out. Might be the x, might be the y. It's up to us, dealer's choice. And say, okay, I want to get rid of one of the variables. I'm going to multiply one equation, maybe both equations, by coefficients so that if I look at what's in front of that variable, it's the same magnitude, different sign. And now what we can do is we can add the two equations together. That will produce a new equation. That equation must also be true. That's this last bullet point. But what's happened is that equation is smaller. It has one less variable. A variable's been eliminated, and so we can solve. We still have that very pesky fourth step, but then profit is in our future. All right, so let's try this with an example. X plus 3y equals 11. 2x plus y equals 7. Do you want to eliminate the x, or do you want to eliminate the y? There's not a wrong answer. It's just a matter of which one do you prefer. Sometimes some are slightly easier, but again, it's not a wrong or right answer. It's just what do you feel like. So x or y, what do you want to eliminate? Don't worry, we have plenty of time left in class. You can still think about it for a while. X or Y, what do you want to eliminate? Y! Very good. All right, we have a choice. Okay, someone has said, well, I want to eliminate the Y. Okay, so let's look at the Y's for a second. We have chosen to eliminate the Y's. So to get to that stage, what we want to do is essentially add two equations together in such a way that the pieces attached to the Y's disappear. So I want to have what's in front of the y's be the same size but different sign. So I look at what we currently have. There's one with the 3 and one with the 1. All right, they're not the same size, and they're the same sign, so that's the problem. So we need to scale. Now we can scale one or both. I claim this time, I think we can get away with just scaling the second one. So what do I want to multiply the second equation by? So here's the question this is our scaling factor. What do I want to multiply by this scaling factor so that what's here, when added to 3y, becomes 0? What does that? So what plus 3 gives us 0? Minus 3, right? So if I can make what's in front of here a minus 3, life is good. We still have the first equation. So x plus 3y equals 11. We distribute the minus 3 to everything. Minus 6x, minus 3y, minus 21. Now add the equations together. When we add in the x's, what do we get? X minus 6x, also known as minus 5x. When we add the second part, the y's, 3y and negative 3y, what happens? 0. And that is by design. We caused that to happen. We wanted it to happen. We wanted to get rid of a variable. So that's good news us. 11 plus a negative 21. Negative 10. So we now have a simpler problem to deal with. All right, but it's a one equation, one unknown. Divide both sides by negative 5, and we get that x equals 2. All right, so x equals 2. Woohoo! Are we done? No. But we're close. What do we do with that? Well, now that we know x, we come back and we just pick one of the first equations. It doesn't matter which equation, and we solve for y. Do you want to use the first or the second equation? And again, it doesn't matter. We just have to pick one. First equation. If we plug it into the first equation, we get 2 plus 3y equals 11, or subtracting 2, 3y equals 9, or divide by 3, y equals 3. So we get our solution, x equals 2, y equals 3. All right. Well, solve by elimination. Do you want to do it? Do you want to take a minute to do it yourself first, or should we do it together right now? Let's do it together, because we do have one more thing to do. All right. Same ideas. We're going to knock out a variable. What do you want to knock out, the x's or the y's? X. All right. We're going to knock out some x's. Now, we look at this and say, and then we say, followed by, Right now, they don't look very compatible in terms of knocking out. So we say, okay, we want to scale. So currently we have a 3 and a 2 in front of the x's. And we think about, okay, what's something that I can scale by? What's a common target to shoot for? So maybe think of what's something that both 3 and 2 go into? 6. So let's shoot to get a 6. One of them will make a positive 6, one of them will make a negative 6. So let's make the first one the positive one. What do I need to multiply 3 by to get to 6? 2. What do I have to multiply 2 by to get to negative 6? Negative 3. All right, so these are our scaling factors here. So our equations become 6x plus 8y equals 14, and minus 6x plus 9y equals negative 48. We add. Because we chose wisely in how we scaled our equations, we're going to eliminate the x. The 6x minus 6x gives us 0. 8y plus 9y, 17y. 14 subtract 48, calculators are perfectly allowed, negative 34. So that tells us, aha, y is negative 34 divided by 17, which is negative 2. So we're like, cool, we know part of our answer. Now how do we get the rest? Well, we're going to take this information about y, that we know that y is negative 2, and go back to our original equations. And we pick one, doesn't matter. Let's say we pick the second one. So the second one says we have 2x minus 3 times y, which we can replace by negative 2 because this is y, equals 16. Or 2x plus 10 equals 16. Or 2x equals 6. 2x plus 6 equals 16. 2x equals 10. I'm sorry. I got ahead of myself in the computation. Minus 3 times minus 2 is 6. Aha! I corrected my error before it became a mistake. Or x equals 10 divided by 2 is 5. If in doubt, you can always run back in. And hopefully we got the same answer after we fixed ourselves. And why should we expect to get the same answer? Because we're just solving the same equations. Regardless of what process we chose, our answer should be the same. So any questions about substitution, elimination? Is one better than the other? I tend to prefer elimination. We're going to discover ways to automate that process. But it's not that one is necessarily better. They're just both options you have available to you. All right. Well, the last thing that we want to do is to say, why are we doing all of this? Well, because there's applications. This shows up frequently. And in some sense, I like to think of it in the following way. When I have one equation and one unknown, I get one knob I get to play with. And so, in essence, if I only have one knob, there's not a lot I can do. I can satisfy one constraint. But when I have two unknowns, that gives me two knobs I can start playing with. I can change the dial in two different ways. That gives me more freedom. It gives me more possibilities. So here's a problem. You're trying to eat healthy. And so part of your diet, you drink milk and orange juice. And you need to make sure you get enough of two things. Enough calcium and enough vitamin A. You know how much you need. You need 500 milligrams of calcium, 1,200 micrograms of vitamin A. And because milk and orange juice are not the same thing, they have different amounts of calcium and vitamin A inside of them. So there's different amounts, right? So orange juice, not great for calcium, but great for vitamin A, relatively speaking. Milk is pretty good for calcium and not too bad for vitamin A. So now there's the question, how many ounces of each should we consume? So the goal is we want to meet our nutritional needs. How much should we do? So we need to set up some equations. So we have some unknowns. So the unknowns is how much milk should we have? How much OJ should we have? We need to provide names to these things. What do you want to call the amount of milk that we need? We can call it anything we want. Do you have a preference? We can be boring and go with X again. All right, we'll go with X. So let's say the amount of milk we consume, we'll call this X. And OJ, we'll call that Y. So we need to satisfy two things. We have our calcium requirements. Now, when we talk about X and Y, these are ounces. So for calcium, we'll take 37 times X plus 5 times Y. And that's how much calcium we're getting. Because we have 37 milligrams per ounce times X ounces, 5, and that's from the milk, 5 milligrams per ounce, Y ounces from the orange juice, and altogether we need to get 500. For the vitamin A, similar process. We say, okay, how much vitamin A are we getting? Over 57 micrograms per ounce, X ounces, so 57X micrograms from the milk, 65 micrograms per ounce, Y ounces, 65Y micrograms from the orange juice, all total, that's how much we're getting, and that's 1,200. So to satisfy our requirements, that's how much calcium and vitamin A we'll need to get. So what do we see? We see two equations and two unknowns. It's almost like it was meant to be for this lecture. Well, yeah, they kind of rigged it, but that's all right. Now, we have a few minutes left. Is it possible to solve? Well, let's think about it. Let's see if we can do some elimination. Can we do something with the Y? Well, is there something that both 5 and 65 divide into? The answer is they both divide into 65. So 5 times 13 is 65. So if you multiply this first equation by negative 13, and leave the second equation alone, you get 57x plus 65y equals 1,200. That's from your first equation. And then we use our calculator technology. Take 37 times negative 13. We get minus 481x minus 65y equals, and we take 500 times negative 13, negative 6,500. When we add, the y's cancel. So 57 subtract 481. 481. We get negative 424x is equal to, and then we take 1,200. 1,200 subtract 6,500. Get negative 5,300. So we end up with x equals negative 5,300 over negative 424, which is good, because that means we're not going to get a negative number out. And what do we get out? We get out 12.5. So that says, hey, you need to be drinking 12.5 ounces of milk. You can go through and do something similar for y. Once you know x, you can solve for y. But now you have x and y. You should always, of course, ask yourself, is it reasonable? If you had gotten a negative number, you'd say, okay, something is wrong. Maybe something's fundamentally wrong with the problem, or something's wrong with the solution. You can't drink negative ounces of orange juice. All right, that's it for today. We'll see you next time.